The following is a problem posed by Weierstrass back in 1880. The goal is to show that a complex function defined as a series of 1 over z to the n plus z to the minus n is going to converge in two distinct areas, one being outside of the unit circle and the other being inside of the unit circle. So we can go ahead and write our function f, our power series as a function f, taking a sum from n equals 0 to infinity of 1 over z to the n plus z to the minus n. Now there's an interesting symmetry in the denominator that will go ahead and carry over to our total function f. And namely, we have that f of 1 over z is equal to f of z, because upon doing the substitution, we realize that z to the n goes to z to the minus n, and z to the minus n goes to z to the n. So our goal now is simply to show that it converges in one of the two domains. For if we can show that it converges outside of the unit circle, that will be equivalent to showing that it converges inside of the unit circle. And by this approach, whenever we are dealing with things in the complex plane, oftentimes it's most helpful to prove that they converge uniformly. So as opposed to considering just 1 over z to the n plus z to the minus n, we'll instead consider the absolute value, 1 over z to the n plus z to the minus n. Now, 1 is always positive, of course, and we can go ahead and bound this below by a smaller denominator. And so then this will be z to the n minus z to the minus n. And here we're just using a corollary of the triangle inequality to produce a smaller denominator. Note that the denominator will not be 0 because we're on the outer units, outside of the unit circle, we're taking that the magnitude of z is greater than 1. And so this denominator can never be 0. Although when n is small, it might be very close to being 0. And actually, I should mention that we're going to restrict this. I should mention that we're going to restrict this for n greater than equal to 1. N is equal to 0 clearly presents a problem because then both of these are going to go to 0. But in this case, we can remove one term from the series, and that won't affect convergence because that one term is finite, importantly. And so, and I should say the term is going to be finite when we're not on the unit circle. That's why we had to throw out the unit circle. So we can do a little bit of an interesting algebraic trick, and we can simply use the definition as a fraction, and we can say that we'll have z to the minus n minus 1 over z to the n, all exponentiated to the negative first power. And so we notice that in the numerator, we have a z to the n times z to the minus n. That just gives us a 1. In the denominator, we have a z to the minus n times z to the n, which just gives us 1. And then the numerator, we have z to the n minus z to the minus n. And then when we take the reciprocal, we get the original fraction. Then this, in turn, we can simplify it further, is just going to be z to the n minus 1 over z to the n to the negative first power. But this, in turn, because z to the n must be greater than 1, 1 over z to the n is going to be less than 1. So we can further bound this by z to the n minus 1 to the negative first power. And this series, this resultant series, we can prove will converge just by using the ratio test. So namely, the limit as n goes to infinity of u to the n plus 1 over u to the n is then just going to be equal to z to the n minus 1 over z to the n plus 1 minus 1. And asymptotically, I forgot to write the limit again, but you know where it's headed. Asymptotically, this will travel to 1 over z. And this, because z is greater than 1, is less than 1. So now we've proven that the series converges absolutely, that the magnitude of all the terms in the series converge absolutely outside of the unit circle. And so so by our original property, we also have that it converges inside the unit circle. And then necessarily, because we have a power series representation, we are also guaranteed that it is a unique function on the complex plane. So that's the end of this problem.